Now let's look at an application of the dot product. Now, of course, this is one application, but let's look a little deeper into what we can do with the dot product. Keeping the example, we have force and a delta x, and there are many other situations where we want to use vectors and dot products and cross products, but let's just stick with this one. So the same picture we had before, F parallel, the vector F parallel is the vector whose magnitude is equal to this side of the triangle, the projection of F onto the direction of delta x. This little arrow here, I'm going to say, is what we call the unit vector, delta x over the magnitude of delta x. I think that little arrow pointing to the little arrow is confusing. So this thing here is the unit vector delta x over magnitude of delta x. Now let me explain the meaning of a unit vector, or attempt to explain the meaning of a unit vector. If my displacement, if that displacement of that car is 100 meters to the east, then if I divide that, well, first of all, my displacement is a vector. It's got a magnitude of 100 meters and it's directed to the east. If I divide that vector by 100 meters, then it has a magnitude of 1 because I've divided its magnitude, or I've divided the vector by its magnitude. Okay, so the magnitude is reduced to 1, the direction is still to the east because I've divided by a positive number, the direction of the vector hasn't changed. So any vector I divide by its magnitude is going to give me a vector of magnitude 1, maintaining the direction of the original vector. Now that's an advantage because, first of all, we've got this unit vector. We're going to use that in a minute. We know that the magnitude of F parallel is F cosine theta. Actually, the magnitude of F parallel is the magnitude of F cosine theta, but we're going to take care of that. Okay? So we have to have a vector whose magnitude is F times the magnitude of cosine theta in order to have the vector component of F in the direction of delta x. If we multiply this quantity by the unit vector, then we get a vector whose magnitude is the magnitude of F cosine theta. And in addition, it's positive if cosine theta is positive. Cosine theta being positive anytime the vector has a component in the direction of delta x, and negative if cosine theta, if theta has a component, well, if F has a component in the direction opposite delta x. So F parallel is going to be F cosine theta multiplied by delta x over the magnitude of delta x. And we have a name for this. We call this the projection of F on the vector delta x. So this is projection of F on delta x. Now this projection is easy to calculate. How do we get F cosine theta? Well, F without the vector, or without the arrow over it, stands for the magnitude of F. F dot delta x is magnitude of F, magnitude of x cosine theta. So if we divide F dot delta x by the magnitude of delta x, we get F cosine theta. So again, F cosine theta is just what we get if we take the dot product F dot delta x and divide by the magnitude of delta x. So instead of F cosine theta, we can write this term. Those are parentheses, not absolute value signs. And then that's multiplied by the unit vector. So this is F cosine theta. This is your unit vector in the direction of delta x. Now let's just do an example. Let's say that your force F is 40 newtons in the I direction plus 30 newtons in the J direction. And that your delta X is 50 meters in the I direction and negative 10 meters in the J direction. So you could adjust this picture. This vector would be a little closer to horizontal if your x-axis is in the horizontal direction, and this vector would be a little bit below horizontal. Your F delta X is easily calculated. It's just using what we used here, I component times I component, J component times J component. So we have 40 newtons times 50 meters plus 30 newtons times negative 10 meters, and that's going to be 2,000 Newton meters minus 300 Newton meters, which is 1,700 Newton times meters. Okay, now I stopped to write a little bit more up here and to go on, and I forgot where I left off. So I might be repeating myself. Just means that I'm probably talking without being conscious of doing so. But I'm going to point my way across this again. The F parallel that you get here, the F parallel vector, is F cosine theta times delta X over the magnitude of delta X. The F cosine theta being the length of this side of this triangle involving F, and not only that side of the triangle, but positive if the parallel component of F is in the direction of delta X, negative if it's opposite. The delta X over magnitude of delta X is just the unit vector in the direction of delta X, which when multiplied by F cosine theta is going to give you this vector F parallel. Now F cosine theta, from over here you can see very easily that magnitude of F cosine theta is going to be F delta X divided by magnitude of delta X. There's our F cosine theta, and our unit vector in the direction of delta X is just delta X over magnitude of delta X. And this thing is called the projection of F on delta X. Now, we're going to do a sample calculation up here. Let's just say that F is the vector that has an I component of 40 newtons. That means 40 newtons of force in this direction, and the J component being 30 newtons in this direction. So I'm pushing off in this direction somewhat. And I'm not sure how well you can see those directions in a two-dimensional image, but I think you can get the idea. And let's say that delta X is 50 meters in the I direction and negative 10 meters in the J direction. So we're kind of going off in that direction. So the force is here, the displacement is here. Then F dot delta X is easily calculated. The I component times the I component is going to be 40 newtons times 50 meters. The J component is going to be 30 newtons times negative 10 meters. The result being 1,700 newtons times meters. Now we haven't talked about work or the unit of work. I'll give you a little preview. Newton meter in this context is called a joule. And that's the unit of work. A joule per second is a watt, and we'll get to all that very shortly. Another calculation then, and this is the work done in applying that force through this displacement. Magnitude of F is what? Well, we just do the Pythagorean theorem, square root of the square of this plus the square of this. That's going to give us 50 newtons. And I didn't have room to write it down, but the magnitude of delta X is going to be the square root of this plus the square root of this squared plus this squared. It's going to be the square root of 2,600 meters squared. That's going to be pretty close to 51 meters. So if I want to calculate the angle between this force and this displacement, the angle between the direction in which I'm pushing and the direction in which that car or whatever it is moving, calculate it fairly easily. Let's look back at the definition here. The cosine of theta is going to be F dot delta X divided by magnitude of X times magnitude of F times magnitude of X. so that theta is going to be the inverse cosine of this divided by this. That's what I've written down here. F dot delta x divided by magnitude of f, magnitude of delta x, inverse cosine of. Now, that's going to give us the inverse cosine then of 1700 Newton meters divided by magnitude of f, which is 50 newtons, multiplied by magnitude of delta x, which is 51 meters. And that comes out pretty close to 0.68, which is pretty close to 0.7. Knowing that the cosine of 45 degrees is 0.71 approximately, square root of 2 divided by 2. 0.68 is pretty close to that, not quite up to it. That tells me, looking at the circular model, the cosine, the angle, the value of the cosine increasing as the value of the cosine decreasing as the angle increases. Anyhow, we see that our angle here is going to be somewhat short of 45 degrees, and I've made the estimate 42 degrees. You can have fun by dividing this out and seeing how much I missed that. I'm pretty sure I'm within a degree or so. Okay, just an example of how you would calculate an angle. The F parallel vector, that is the projection vector, equals what? Well, I put an etc. there. I'd let you calculate it. I would recommend calculating f dot delta x over magnitude of x and comparing it with some of these quantities here, and then your delta x over magnitude of delta x, and thinking about what those two quantities mean, this quantity being a numerical quantity. It'll come out with units of force. This quantity being a unit vector. Yeah, it's going to have to look like a unit vector. It's going to have components less than 1, etc. And you might think through that just a little bit. So what I've done here is I've given you what the book gives you and a little more. I talked about this projection because that's the main application of the dot product. If you don't understand the projection right now, it's no big deal. But to get an intuitive grasp of what all this means, you're going to eventually want to be able to understand that. So this is worth another look, maybe a little bit later if you don't understand it immediately. If you understand it right now, so much the better, because it will be used within the course of the year.